Hello, everybody. Welcome to Robert Gatenby, who I will be referring to as Bob. Welcome to his Q&A session. We are here just to make, I am here just to make sure that everything runs smoothly today. So the only thing I'm going to ask of you all is that you stay on mute if you are not currently asking a question. That's just going to make sure that there's no feedback or anything disruptive happening during the call. And please let me know in the chat if you have a question. I'll call on you and give you your time to ask and get your response from Bob. Bob, take it away.
Oh, well, good afternoon, everyone. Henry, I see you there. How are you? And then we have a few others. You want to just, I don't know whether we have any questions that have been asked yet, but I don't know. Henry, do you want to, did you have something you wanted to ask?
Okay. First, enjoy your talk because
thank you.
Your pioneer work of this field. We all hope, that somehow your work will convince the majority of people so the evolution works. So I have a couple of questions. Maybe I just ask one first. So we did the drug resistant experiment. So we always found that the induced new altered genome is much more powerful than the original competitor in such a way. So because for a long time, we thinking the population genetics is based on stepwise, gene frequency replacement, such a framework. But now, in just few hours or 24 hours, the induced massive change is completely not to follow the law of previously we thinking how the evolution is working. So therefore the my question is, do you think if you consider the if you have different phase of evolution, if you focus on micro evolution phase, and that actually could further improve your adaptive therapy in terms of to avoid to induce this potential monster?
Sure.
So this is the first question. Maybe yeah, to get you.
Oh, sure. I mean, I think there's a lot of things that we could add. We've started off very simple, and of course, we're dealing with hormone replacement, so we probably are not applying a large mutagenic load to the tumor, although I suppose we may. But what I think though is that it's important to get out ahead of the tumor, so that if you are using something that's mutagenic as a therapy, then anticipate that and see if you can exploit that somehow. So if the tumor is adapting by doing that, then perhaps that's the time to add immunotherapy when you have a lot of new antigens being presented in the tumor, or perhaps that's the time to look at HDAC inhibitors or something like that that may even enhance the mutation rate and develop this sort of error catastrophe as a potential option. So these are all fascinating options, and one of the things that we've been doing then is to develop, since we start with math models in the patients to begin with, we can then look at all of the models individually and then sort of go backward and say, well, what did we do right and what did we do wrong? We can also take those models and start to add additional dynamics to it. So suppose we were to do this, what would happen? And the goal is to really go from a kind of a passive approach, you give a therapy and then you wait and see what happens, to a much more active approach where you take you as the therapist always takes the initiative, is always sort of attacking the tumor, anticipating response, using that knowledge of evolution to your advantage rather than letting the tumor just kind of evolve resistance and letting it happen.
Sure. So the follow-up question, years ago, I read some of your paper, you're talking about just like the constrain the system, right? For example, you do not want to take away all the tree and then later another tree going. So if you're thinking that way, for your clinical trial, sometimes, or even for animal model, so when this animal individual failed, so what's the profile for this? I mean, the individual who did not follow the expected by the adaptive therapy. So is this individual have unstable genome? Have you guys tried this one? Because we actually tested the patient. We found someone is extremely unstable, someone is fairly tolerable. So we anticipate when the genome unstable, so you under the same dosage of treatment, they may trigger the extremity. So have you guys profiled this individual?
We have not yet, but I think you raise a really good point, is that we often, what we characteristically begin therapy with a very incomplete understanding of the evolutionary state of the tumor. We don't really know initial conditions. And I think it's important to understand that greater information about initial conditions, about the dynamics of the tumor, can be used to optimize therapy. And if anything that I've learned from this is that we don't know enough at the beginning. In prostate cancer, for example, it's very hard to do biopsies because most of the time they have metastatic disease in the bones, and those are very painful to biopsy. And yet, what we're learning, I think, is that if we knew more, we could do better. And so maybe we should be, accepting that the biopsy, though painful, provides extremely valuable information, and we should go forward with it anyway. So anyway, that's kind of my initial.
Okay, thanks. I will let other people jump in. Yeah.
Okay, sure.
All right, if anybody has a question, you can either let me know in chat or pop yourself off of mute and go right ahead. Hopefully, we're not having a bunch of jumping over each other. We will welcome any questions, big or small. And Bob, if we don't have any questions right away, feel free to elaborate on your talk. Obviously, everybody is already very interested. So,
sure. We should. I don't think I mentioned that we have a trial going on in pediatric fusion-positive rhabdomyosarcoma, where the goal is cure. The goal is to use the extinction therapy that I described in the talk, with the goal of curing these kids. That is a multi-institutional trial that opened about a week ago. We have a second trial for adaptive therapy in castrate-sensitive prostate cancer. So this is androgen deprivation therapy used turned on and off. Men hate androgen deprivation therapy typically, and so they're happy with the not having the constant side effects of it. That's interesting because the dynamics are actually slightly different than we saw in the abiraterone, primarily in that the cycles are longer than what we saw. And so that trial has been going on for 4 years, and we still don't have a patient that's progressed. So we don't have a single data point on that, but I think it's likely that they're doing pretty well compared to what you would expect given a standard cohort. We have another trial, and I think I mentioned this in my talk, that androgen deprivation therapy almost always, greater than 90% of the time, can reduce the PSA to normal or even undetectable. So it is a very good first strike in terms of the androgen extinction model. And so we have another trial going on in which the after androgen deprivation therapy, at the trough of the PSA, we will apply second strikes of curing them. So we have a couple of those going on. Another trial, the androgen deprivation therapy trial, and extended to Emory now, and we have a few other places. doing this. And a few places are their own trials, although, it's honestly been a very slow uptake among the oncologists.
So I have one more question. So for the adaptive therapy, so if you're thinking about the evolutionary constraint at a higher level, so if we outside the tumor, if we want to put the constraint, do you think the treatment should be more specific towards the target, or actually should be less specific? Because if you're thinking, yeah.
I think you can design strategies either way. The answer is I'm not really sure. It would depend on what alternatives you have. So sometimes you can use this. So to give you an example, one of the things that we've explored computationally is suppose you were to give, let's say we'll go with abiraterone. When would you give, and suppose you have a chemotherapy that would be effective, and when would you give it? And so one modeling approach has been, so you give them abiraterone, and as the PSA goes down, give them dose or two of, say, docetaxel, a cycle-specific chemotherapeutic agent, reasoning that while abiraterone is present, the only cells that are going to be cycling, they're going to be undergoing mitosis, are the ones that are resistant, so that you're selectively punishing the resistant ones. So you have a relatively specific first strike, initial kind of approach, and then you add a rather non-specific second approach, where you're sort of, punishing resistant. An alternative is to take, so for example, suppose you have you're using a chemotherapy, and the cells that are resistant are using P-glycoprotein. So you could administer so one of the approaches we've taken is to say, give the drug, lower the tumor volume, withdraw the drug, let the tumor go back, but add a substrate for the P-glycoprotein that's non-toxic. So then, as the tumor is going back, the ones that don't have the P-glycoprotein are not dealing with this that you've added, but the ones that are pumping it. They have to use a lot of energy to deal with it, even though it's not not cytotoxic. It is a substrate of the pump, and so you're forcing them to use energy, which reduces their fitness. So that you're extending the difference between the resistant cells, and you're giving the sensitive cells an advantage, so you can get them back to where you are. So what I can say is you can, once you've got this sort of idea in your head, you can stay up nights thinking about diabolical ways to correct the cancer cells. And it's actually kind of fun, although you lose sleep over it. But you get the idea. I mean, you can start to put together lots of different strategies that you could imagine giving the patient an advantage by playing with the evolutionary dynamics. So what I've shown you, the adaptive therapy, for example, is just an example. And I try to be clear about that there's many ways you could do this. This was an easy example that could be translated readily into the clinic. But there's others that are more difficult to translate, but maybe more successful. So one of the things that we've talked about is converging into this kind of situation where what you do is simply try to keep the tumor stable. You don't try to, you just touch it a little bit, just keep, that sort of thing. The models suggest that may be actually the most effective way to do this, but it's practically very difficult in a clinical setting. It would require kind of a different approach.
Mm-hmm. So Another actually related question is, we actually found that if you use a different multiple hit for the cancer, so you hit one, and then the second one you hit actually doesn't matter which one you use. So because that's kind of fits what you have talking about.
Yeah.
So therefore we are thinking maybe we should use even including lifestyle change if the regular to fit for the system.
Absolutely.
Therefore,
Absolutely.
we can have the second or third hit, which is not drug at all.
Mhm.
So is that you think you can entertain that?
Yes, and we've talked, so there's a couple of ways to do this. One is, of course, the demographic perturbation, so that you're killing the tumor cells in some way. But there's also environmental perturbations, which means that you're changing the environment, and they often engage in these engineering, ecological engineering kind of approaches, where they change the environment for their benefit. And some of it's just very simple, like angiogenesis. But so if someone can exercise while they're being treated, and they can develop a little bit of acidity, their blood pH goes a little bit lower, that can translate into an enormous change in the pH of the tumor, which is already acidic, and requires the acid concentration gradient between the tumor and the blood vessel removal. That's the dominant way that it's removed. And so subtle changes in that can actually cause very dramatic changes in the tumor pH. So, this kind of, if you could greatly acidify the tumor for an hour or two, you have a strong negative effect on the cancer, potentially. And any number of other lifestyle things. And we see that in the patients that are very motivated. We have kind of a cadre of patients who are most commonly they're young women, actually. A lot of them have metastatic cancers and they are deeply motivated to survive for their children, and they really want this. And so they, as a group, also engage in a lot of different lifestyle changes. And knock wood, so far they've been doing pretty well with this kind of extinction therapy, approach. But that's just kind of a informal. I mean, it's not a trial or anything. It's just, what they want to do because they want to do it. So.
We lost you right there at the end. Do you mind repeating that last sentence? It sort of muted out for a second.
Oh, I'm sorry. So I was just saying that there are people that are doing this kind of extinction strategy, and they're engaged in they're all very motivated, and they're very they read everything. A lot of them are physicians, actually, and so they on their own have also engaged in a wide range of lifestyle changes, diets and fasting and exercise and those things that I think can be viewed as environmental perturbations in the tumor, and without systematically knowing what they're doing, at least we can classify them in terms of a potential impact.
Thank you.
Gatenby, first, congratulations for your work that I've been
thank you.
Years, and it definitely applies to some patients. So my question is the following: different cancers behave differently, and the extinction type of approach, I think it fits leukemias, aggressive lymphomas, testicular cancer, choriocarcinomas, where you can give high amounts of chemotherapy and really cure the patients. And of course, at the other end of the spectrum, you have some cancers that are more indolent, like prostate cancer. And I completely agree that in some of these cancers, the adaptive approach is clearly better than the extinction approach. I was wondering if there is some type of biomarker where you can identify some of the cancers that are more prone to the adaptive approach in terms of the growth curve or something like that. And secondly, if in some of the tumors you can apply a combined approach, like an extinction adaptive approach. So you extinct, the big mass, and then you use your adaptive approach and something like that. Coerce strategy,
Yes. Well, that's, what you're talking about is a thoughtful and dynamic approach. And I think the answer to all that is yes. When we look at what are the major determinants of outcomes in terms of the different strategies, and this goes to Henry's question a little bit, it's the evolutionary rate of the tumor. If the tumor can evolve very quickly, we need one sort of approach. If it evolves very slowly, we need another approach. Now, that's a wonderful term that you could use in mathematics, but quantifying it is quite difficult, and is going to require, again, some detailed pre-treatment investigations. I think you probably were not on when Henry and I were speaking, but one of the biggest conclusion I have is, first, we need to understand the evolutionary state of the tumor as an initial condition before you begin treatment. What do we know about it? What are its conditions? What are its clear dynamics that are dominant? What we find is that in some cases, maximum tolerated dose, the conventional therapy is the best approach, and other times it's not. And all of this is really, I think, meant to take the idea that this is a patient-specific approach, that in addition to molecular targets, precision medicine should also be thinking about how the disease evolves, because that's very specific to the patient and the treatment. And those kinds of things are not what we typically look for. So it's really, the goal is to not be dogmatic. There's going to be, there's not going to be a single way to do this. Adaptive therapy is one way that you can approach this. And in prostate cancer, which looks like it evolves rather slowly, that works pretty well. And in something that evolves very quickly, and melanoma, for example, might be an example of that. It's unlikely that if any delay, any lapse in therapy, the tumor can get out of control, and so that may not be the right approach, in that setting. But it's likely that in most cases, a thoughtful application of evolutionary dynamics will improve patient outcomes compared to the opposite of not considering.
Thank you. I think that the key question here is how much to give in this adaptive approach. So you basically are destroying the bad guys and you're leaving, some of the better guys, and what dose to use. I mean, this is, I think, is the golden question in the field.
Mm-hmm. So in the trials that we've used so far, what we've done is used the standard dose, but applying it briefly. So, for example, androgen deprivation therapy, we apply it until the PSA is dropped to 50% of the treated value, and you stop. So it's on, off, on. In preclinical models, what we did was to say, you have a tumor that's growing really quickly, so you've got this sort of almost exponential growth curve. First, whack it really hard and turn it onto a plateau. Once you have it on a plateau, then reduce the dose, and just keep reducing the dose until you've got it stable. And we were able to do that very successfully in a preclinical setting. In a clinical setting, that's much more difficult, as it turns out. So we kind of negotiated how to do this with the clinicians. It was really clear that kind of approach, although theoretically superior, is harder to do. So, and we would, at the beginning, this was really just minimizing risk. What we wanted to do is to do a protocol that would not cause a lot of trouble for the patient, and minimize the risk of a catastrophic outcome. And so we had, we had stopping rules at the beginning to just make sure that if anything bad happened to a patient, we would withdraw this and go back to the drawing board. So I think once we have gained some confidence that the dynamics that we're looking at, the dynamics we predicted at least are, are present, that we can see those, then I think we can start to look at more creative and perhaps more difficult strategies that would perhaps work better. And so for the very aggressive cancers, like MB231s and very rapidly growing breast cancers in our models, we could control them very well, but that required first getting it under control and then using lower doses rather than time points.
I have a couple of questions, if you don't mind.
Sure.
And maybe they are naive, I'm not specialist. So for applying the adaptive therapy for prostate cancer treatment, would you recommend that instead of prostatectomy, for example, which is a bit drastic and has an impact on the quality of life of patient, or do you see it as a complement that comes after the prostatectomy? The second question is, for a patient who has castration resistance or have metastatic prostate cancer, do you see the adaptive therapy as still effective? Because at that point, we may think that the resistant clone is already selected for. So do you see the therapy as that could still work in these scenarios?
Yeah, so to be clear, all of the trials that we've done have been on metastatic disease. We only want to deal with patients that we know are incurable, and did not want to take any risks on any patients that are potentially curable, so that we didn't reduce the probability of that outcome. And so all of the trials that I've talked about have been on metastatic disease.
Okay.
In prostate cancer, sarcoma. Okay, so as for treating primary tumors, I'm generally reluctant to get involved in that right now, because it just feels like it's there's a risk of doing harm. One area though that we've started to get involved in quite a bit is in adjuvant therapy or neoadjuvant therapy, where you have a high-risk primary cancer, but no clinically evident metastatic lesions at the time of treatment. And it's become quite common that they are given therapy either before or after the removal of the primary tumor, with the goal of eradicating microscopic populations, and so preventing subsequent development of clinical metastasis. And that very much is along the lines of the dynamics of small populations. And so there, your explicit goal is, in fact, to kill small populations. The results of adjuvant therapy show that you can reduce the risk for metastatic cancer. So that it's clear that you can eradicate these small metastatic populations, and yet in most cancers and in most of the times, they don't do it. The metastatic lesions actually do develop. And so it seems to me there's a lot of room for improvement. And so just to give some examples, it's time is of the essence for this. So if you remove the primary tumor and then you're going to give adjuvant therapy, we think it's very important to give the adjuvant therapy as soon as possible, and preferably in the neoadjuvant setting. You're going to, in other words, begin therapy as soon as you've got the diagnosis made. But if you're going to delay it, you should not delay. If you're going to wait till after the primary treatment, the primary cancer is removed, you should begin quickly. And then the second thing is that right now the adjuvant therapy is given as basically the same treatment over cycles, 3 or 4 cycles. And we don't think that's a good idea. I mean, again, you simply keep applying the same chess move, and the tumor can respond the same adaptive strategy move each cycle. And so we think that it's important that adjuvant therapy be given as a sequence of different treatments, so that you're essentially attacking the tumor in multiple different ways, rather than therapy over and over.
Okay. So you don't recommend using ADT treatment in an adaptive approach like you described for patient where the patient doesn't have a resistant yet?
No, so we have a trial going on with androgen deprivation therapy and metastatic castration-sensitive prostate cancer. So this is first line therapy. We've had that. It's an interesting trial because we started with abiraterone, which is the treatment for the metastatic castration-resistant prostate cancer. But once it was clear that that was getting a good outcome, we went to metastatic castrate-sensitive prostate cancer. So this is first line. What we found in the castrate-sensitive group is that their cycles are longer than what we'd seen in the castrate-resistant population. But it's interesting because this trial has been going on for 4 years, and not a single patient in the trial has progressed yet. So, and I mentioned we have no data points essentially on this trial, but it does seem like the outcomes thus far are quite positive. So, just as an aside, we're now sort of looking at strategies that allow you to merge androgen deprivation therapy into the second line treatments, with the goal of now having strategic linking of 2 different treatment approaches, but with the goal of long term melding them together so that patients are treating. So in your first protocol is treating with the expectation of a second protocol, and so the treatment is designed with follow-up in mind.
Okay, thank you.
May I make a comment? First of all, I wish to apologize because
Sure.
There has been a problem with the timing, and I joined probably an hour late. And I was interested in listening to you. By the way, I'm Carlos Sonnenschein. I was interested in listening to you, not from the clinical point of view, but from the theoretical point of view. You adopt this idea that there is a selection at the level of the organism, which is, let's say, a controversial issue, as you probably are aware. And I was wondering whether you could talk about that if you haven't, and tell us why do you think there is selection within the organism? In other words, is there a theoretical basis for that, or a practical basis for that? Because I understand that your therapeutic approach is based also on that premise, right?
Yeah. So the selection pressure is on individual cancer cells. Is that? I just want to make sure I understood the question. So we view the individual cancer cell as the unit of selection in the Darwinian dynamics of treating cancer.
Let me start from the normal, let's say, because if I read you correctly, what you are saying is that there is a competition between cells within the organism to get ahead.
No.
Let's say, quote unquote.
Okay, now I understand the question.
So, as I said, that premise is somewhat controversial because, at least in my case, I don't see why my brain cells will have to compete with my kidney cells. So now that I have you more or less in person.
Now I understand the question. Okay. So no, we don't think that normal cells compete with each other. In a multicellular organism, the unit of selection is the organism. The cells, the cells are, you can view them as traits of the organism or something like that. So ordinarily, the cells, normal cells, because they live and die based on instructions from the organism, do not evolve. They are under the control of the organism. They are part of the organism's fitness function.
So they don't go.
The transition to cancer is what's really interesting, and this really. Go ahead.
No, what I meant and sorry for the interruption.
No, it's okay.
What I was interested in, let's say, listening to your explanation why you claim that there is selection, or at least that is the impression I got from reading your papers.
So,
yep.
So we view cancer cells as a transition from a cell that is part of the fitness of the multicellular tissue of the multicellular organism to one that has its own fitness function. So now it's a self-defined fitness function, meaning that its birth and death are dependent upon its properties and its interactions with local environment. And so these cells can evolve. Unlike
we are having problems
cells,
of
which are not.
Your speech is blanked sometimes.
Okay, I'm sorry. I'll try to. So I'm not sure where I left off here, but so every normal cell has the fitness function of the organism. Its birth and death is dictated by normal tissue constraints. So it is under control. So we define a cancer cell as one that has made a transition to a self-defined fitness function. So it is no longer controlled by normal tissue constraints, and its proliferation is dependent upon its properties as they interact with local environmental selection forces. So it can now evolve. And so what we propose is that the fundamental difference between a cancer cell and a normal cell is that a cancer cell can evolve. And it competes against other cancer cells during that evolutionary process. But normal cells do not compete with each other and do not evolve. This has implications for the mutational kind of the mutational model of carcinogenesis, where it occurs as a sequence of mutations. We think that it's quite possible that the initiating event is actually a normal tissue function decline due to injury or infection, and it releases cells that are no longer under control, not because they are blind and deaf to the tissue constraints, but because the tissue isn't making those constraints, which is a subtly different approach, but would explain why, for example, cancer cells have the same mutational burden as normal cells in the same tissue. So the argument is that you can have mutations but still be not evolving because you're still under the control of the normal.
But that argument in a way rules out the somatic mutation theory.
Yes.
Because if you have mutations and they don't do what you expect, which is what the somatic mutation theory proposes,
yeah,
then you falsify the somatic mutation theory. Now, at the same time, in your narrative, I can pick up that, I mean, it's well known that these cancer cells, or what they call cancer cells, can become normal cells. In other words, it is a reversible process, contrary to what the somatic mutation theory proposes. I don't know if you agree with that. In other words, that a cancer cell can become a normal cell.
Yeah, I think that I've spoken to Mina Bissell about those. I think you're referring to her experiments. That if you take a malignant cell, put them in normal tissue, they can become normal. She describes this as a continuum. In other words, it's not all the time, but early cancer cells seem to still be potentially controllable. As they go further, it becomes more difficult. But nevertheless, the observation that if you take a cancer cell and you put it in normal tissue where the normal tissue constraints are functioning, and it becomes normal, it would suggest then that the emergence of a cancer is not fundamentally about mutations. It's really about the interactions between the cancer cell and the normal tissue. If you have, for example, our skin has a lot of mutations present, including oncogenic mutations. Once the cell is no longer under control, those mutations can contribute to the fitness. But they do not contribute to they can't contribute until the cancer cell has acquired a self-defined fitness function. And that may be because of the tissue, not because of the cancer cell. So I think that the model for carcinogenesis that's based on mutations is incomplete. I mean, I think it can happen, but I think that the role of the tissue in constraining what otherwise would be a malignant cell is something that we tend to not think about. If you go back to the 50s, during the old cell, where they used to do what was it was called, they would add a mutagen and then they would add motion progression.
The progression and
yeah,
let's say initiation and progression.
Initiation, right? So if you put a mutagen on, you can radiate or do whatever you want. You can make the cells have mutations, but traditionally they were phenotypically normal. You couldn't distinguish them from the adjacent tissue. It was only after you caused inflammation in the tissue, or you injured it, or you did something like that a tumor began to emerge. Which to me, that suggests that you damage the normal tissue. It loses control of these cells. They can begin to evolve and proliferate. But most of the time, when the normal tissue in that setting repaired itself, the tumor went away. It was only after progression. So there's that additional evolution that's required for that cancer cell to become completely independent of the normal tissue. And I think that I don't know why we don't use those experiments. I mean, I remember, of course, it shows my age. I remember people used to radiate their arms with ultraviolet radiation to make cancers grow, and it's part of these experiments. And that whole that whole research endeavor, which was so popular in the 50s and 60s, has been almost lost in the rush to look for genetic changes. So anyway, I just think that I'm not so I think we agree. Probably no one else on this audience does, but I think we
more or less
are agreeing that the somatic mutation model of carcinogenesis, as popular as it is, has some limitations that I think still should be used.
I agree, but I will add one layer of complexity. I think that is not only the tissue that controls, but is really the rest of the organisms that controls. It's not only that tissue, but I think you have also the immunity, you have
Oh, sure.
system. So it's not purely the tissue that controls the appearance of cancer, but I think it's a global system of the organism. So you have a cancerized organism, not only a cancerized tissue.
Yeah. And this has important implications for prevention. You know, if we focus on the tissue and the organism rather than the, making, keeping that more intact rather than just on mutations, I think we could see some interesting different approaches to prevent.
So I have one more question. So Bob, back to your model. So when you're doing you did a lot of mathematical modeling to see the landscape change. So for your adaptive therapy, if you want to specifically target the outlier, do you need to use more force or less force? Or if you want to use control the average landscape, so we actually try to separate these two. One is, so what's your view?
We wimped out as we designed the clinical trial. So why did we choose 50%? So PSA starts at 50%, we stop. Because we were wimps. We were afraid to really put our money down on any particular number, so we went for the average. And we know now that we've analyzed the patients that was not the best approach, that we really should have done much more, that there should be much greater variation in it. But we were afraid of a catastrophic outcome. And so we were very wimpy about what we could do. And part of it was, the best approach really would have been much shorter period of time. You give a therapy, you wait for the PSA to go down 10%, 20%, then start and then let it go again. That would have been, and we kind of knew that, but the problem was that that would be inconvenient to the clinic. It would require more frequent measurements. It would require the patient coming in more often, and would cause greater inconvenience than would be necessarily tolerated in a clinical setting. So we went with this kind of middle number, and I think now, given that we have some success, we validated this would happen as the models predicted. I think we will probably go toward this approach that we would have favored in the beginning. But I cannot tell you how terrified I was in getting this started, because, and I mean this, every patient, I knew what was going on with every one of them, and I knew that as their PSA was going back up and they were going to have to start treatment, I would have nightmares about whether that new treatment would work or not, as predicted. So we took what we thought would be the safest approach, and I think, and so we could have done better, and we could have done worse. So, I think it's okay, but I think having gained this experience, we can now build on it. At the time, we sort of thought it would work, but we weren't really sure, and so it was the level of stress was pretty high for me.
I want to just make a comment about back to Carlos, the questions about the normal environment and tissues. Actually, we just finished a study of the chemotherapy response of the ovarian cancer. So the question is, when you look there, those tumors, there are a couple of changes. Either cell, die, which is most people expect. There are second group of cells, they simply differentiate into a variety of normal cells. Okay, so you can see those,
Yes.
they're not going to really normal pure lineage. If you say ovarian epithelial cells or prostate, they're going to go to other tissue differentiation like macrophages, and also even can generate blood, and then just simply liquid and melted away. So raise trans differentiation into hematopoietic lineages. So simply, part of the normalization. One of the best normalization of tissues is the examples of teratomas, right? Because I showed yesterday immature teratoma,
Yeah.
right? So pretty much you treat the immature teratoma, everything become a mature teratoma. So everything is become normalized. However, after you treat them, then those normal teratomas is going to transform. They're going to become a carcinoma or sarcomas. So this transformation process, if you look at it, and at the very beginning, all those transformation into different histology, this must be mediated by those transient stress-induced giant cells, because this is a program to mediate to different transformation. But you do have all the normal differentiation programs can be activated during various chemotherapies. I just want to make a comment on this.
Yeah, that's very interesting.
Yeah.
What are the things that did you look at the spatial distribution of the cells? What you were really looking at were the survivors after your chemotherapy. Is that right?
Yeah, we divide. We just divide by chemotherapy score, and say if those is really melted away, completed all the tumors away, or all left over is just a scar. It's just fibrous tissues. But people call the scar. Actually, I think those are just cancer cells transformed into a normal fibroblast. So it's a reverse differentiation process. So you can see those kind of cells. So you can call this a speciation. It's not really normal or not. It's a loose term. So how you can define the cells, but you do have a variety of those cells. Some cells becomes very, very active. I didn't have a time to show some of those images. It's just ugly. Tons of those giant cells sit there, and nobody knows what's going on. And but those eventually can really be dormant for many, many years or months, and then those cells they're going to rejuvenate. So this is just you can see it.
Have you spoken to Ken Pienta?
Yeah. We're on the same page. He had been talking about this.
Okay, all right. So, all right. It sounds very much like what Ken has been doing. Yeah, it's very, very nice work.
Yeah.
So, is your thought that take a classically fibrotic tumor like pancreatic cancer? Is your thought that the fibroblasts that are the fibrosis that's part of the pancreatic cancer tumor is a tumor strategy? Are the tumor cells making this? Are they transforming into fibroblast-like cells? Is this a tissue engineering approach where the cancer is making a tissue environment that's maximally favorable to its growth, or is it a host response that's being ineffective?
It's both ways. It's two ways, and it depends in which context. For example, during tumor initiation stage, what we observed actually, those cancer cells just grew out those fibroblasts. So they simply, it's not the EMT, it's MET. Mesenchymal become a cancer cell out of nothing, and then transformed. And then nobody talk about this, but I just wrote the first papers. I described this phenomena because I see it. It's there. You have to believe what you see. Okay, so this become fibroblasts. They transdifferentiate. So the mesenchymal cells, they're good to mesenchymal cell, but the epithelial cell can come out from a mesenchymal cell. So because every epithelial cells, they come from mesenchymal cells. So you have a stromal background. So it's a dynamic process. Those things get messed up, and you favor one way or the other, depends on the context. So if you put too much pressure on the tumors, they're going to go back to fibroblast. So you can see those cells can be transdifferentiated into those fibroblast, or all kinds of stromal cells become normalized, become benign. So it's a malignant and tumorigenic process. it's a dynamic process between benign and malignant. You can see all those features on the microscope. Most people, so they talk about experiments and then they transfer this, they cannot see this. But in real tumors, you can see clearly all those images. You can see it.
So one comment is when Jin Song talking about all this change, also answer Carlos' question. If you check the genome, they're fundamentally different. They all go through genome chaos phase. So that's actually that actually is observation in a way. So back to your question, initially, even though it's a little bit departure from Bob's the subject, but actually the traditional experiment, in 70s when the did this, so-called cancer cell can completely change the phenotype when put into embryonic environment. That is partially because she noticed every time that happens, you have to have normal karyotype. Otherwise, they cannot get back because it become new system. So you go check the 1976, the PNAS paper, even in the abstract, the CITESO, a few years ago, they repeated experiment. They cannot get a normal development, and they found they have some chromosomal change. So the said is not just epigenetic, but the genetic change is real. So we actually need a rethinking all this classical experiment actually to say the information is there. So that's why I think the Jin Song actually his experiment is in the past 10 years really showing the development process. Even though the phenotype they have some different cell type transition, but the genome type they fundamentally actually goes through dramatically change. So that's also is a observation. So that's my the comments.
Yeah, so this is pretty much is either you start from very beginning when your life started, and then you have those whole genome changes because this involve the demethylation, everything, whole genome need to be rearranged. And then before you have a new life, and then for your son, for your daughters. Same thing for pretty much of the cancer, okay? So you cannot really cell just start proliferating by a mutation. Actually, this is a pathology. If you got too much cells over there, this is called hyperplasia. This is not called cancer. The cancer, you have to be immature. And then all those cells has to have those ugly nuclei back to very embryonic stage. This is how cancer is defined, not by too many cells or just tissue, out of context. But this process is really can be switched back and forth under the stress, under the pressure, which involves the whole genomic rearrangement, dictated by Barbara McClintock's principle.
Tannah, I think we're probably. Oh, go ahead.
I have a question, but I wasn't sure if you were going to answer Dr. Liu's question. So go ahead.
No. Go. I think we're just in agreement.
Yeah, absolutely.
Okay. So.
Well, I'm so sorry to interrupt, but I actually have sort of a layman's question. I am not a scientist. I'm just Perry's daughter, so I've heard a lot of things about this, but I am not at all familiar with this. So my question was actually, so what you said was that we think it's quite possible that the initiating event of cancer is normal tissue function decline due to injury or wound. So I was curious what the effect of, say, carcinogenic chemicals in foods or in water. I know that there was recently a study about the chlorine content in water, specifically building up in women's bodies and in their breasts, and that causing breast cancer. And so I was curious, what is the interplay between, tissue injury and carcinogenic chemicals? Like, how does that evolve? How does that work? And I'm sorry if that's not like in your field or anything, but I've been so curious.
I think Dr. Sonnenschein is probably more the person to answer this than I am.
Is that an invitation?
It is, yes.
Okay. Well, I think that is the way cancer evolves. It's only, I mean, I didn't want to reinforce the idea that the cancer is a tissue-based disease, favoring what pathologists used to tell us from the 19th century, starting with Virchow and company. But let's say the idea that there is a cancer cell is something that I have tried to convince the readership that it is fantasy. There is no cancer cell because you can make a cell normal a cancer cell normal in the midst of normal cells. I heard the objections that both Henry and Shunson have made. I still think that it is clear that cancer is, as Dr. Gatenby mentioned as well, is a tissue problem. The reason, an answer to your question, Tannah, is that all these carcinogens, even chemotherapeutic agents, affect the structure of tissues. And that is why, despite the fact that the purpose of using chemotherapeutic agents is to cure, quote unquote, cure cancer, they also generate more cancer because of a number of effects that the chemotherapeutic agents have on the tissue structure. I think that that is why sometimes, let's say, I'm not proposing to eliminate chemotherapy, but chemotherapy is not clearly a panacea, and in many cases is worse than the original cancer.
Carlos,
I don't know if...
can I add it? Carlos, we are in agreement. Cancer is a tissue-based disease, okay? But there's a couple of things I did not agree with you. I have to say, it's a tissue-based disease, but you have to add embryonality in immature tissue to there. It's not just a tissue field, okay? So this is one question. I did not agree with you. It's has to be immaturity over there, otherwise will not call cancer. Okay, so this number one. Second, cancer cell disease, it's a cell disease. This is applies for hematopoietic disease, okay? But we can view as a hematopoietic as a specialized tissue, okay? Because one of the differences between tissue and hematopoietic disease is that you don't have a cytokinesis inside of tissue, and hematopoietic disease do separate in the individual cells. So this is, but at the origin, which is the bone marrows, that's where you generate those. It's still a tissue. So, but we can view those as a specialized tissue type that can generate the individual cell, because leukemia, you see a cell, that's a cell. So, but we should not generalize of tissue-based disease according to hematopoietic disease. It should be other way around. So on the tissue front, we all agree, okay? But you need to add the developmental into those tissue field theory, otherwise it will not hold. That's my opinion.
I would like to know how many scientific papers begin with the sentence, cancer is a disease of the genes. I would guess that there's hundreds of
95, if not 99% of them, even today. Even today. The issue is that, as Jinshun implied, I'm not saying that he said it, he wants to find some type of a compromise. And unfortunately in science, at least in the science that I am aware, it is a benign dictatorship. Today, the somatic mutation theory is the king. Tomorrow it will not be. And the next day, someone is going to replace the tissue organization field theory. But the issue of putting together the somatic mutation theory and the tissue organization field theory is a fantasy because
Okay.
it doesn't work. It doesn't work. Either you have blank or you have, at least in science, and that is the history of science. I am not saying that what I am saying is the absolute truth. I am saying that today, 95% or 99% of the papers, as Dr. Gatenby reminded us, are saying that cancer is a cell-based disease and the somatic mutation theory is king.
Sure.
Well, tomorrow probably is not going to be.
Yeah, so let me actually just clear some of my standard. So Carlo knows, in the past almost 20 years, I have wrote so many papers to be critical to the gene mutation theory of the cancer. So, but the thing is, we also thinking the clinical or sequence fact, because despite the have different highly diverse gene mutation, but they always have many mutations involved in such a way to help the cancer growing. So we actually gradually realize that maybe the initially cancer formed, but then second phase, microevolution phase, they just help them to grow a little bit in such a way. So that is also the fact. So we try to put this together in a way. It's not just, you have to go this way or go to that way. So we thinking the tissue disease, but the tissue, when it becomes disease, they have evolutionary process. If you have evolutionary process, they have to inheritance involved. You have to have some entity which involves the inheritance. So that's actually the way.
That is, if I may, Henry, nobody can claim that the people who propose that gene mutations have a role have had enough time. They have more than a century to claim that, yes, it is this way. They cannot claim that they don't have the funds. They cannot claim that. So, and these people are very smart. Last week, we heard a number of them insisting that there is this gene. And I want to ask, which is that gene? Nobody can claim that they didn't have the chance to tell us which is the gene. What Henry is mentioning is a correlation. Yes, I know. I started my career in science as a cytogeneticist, and I saw all these chromosomal aberrations. I work with somebody who died thinking that chromosomal aberrations cause cancer. There is no evidence for that. It is a correlation.
No,
I want to. I hope you're satisfied.
Carlos,
Thank you.
I'll have to kick in. I'm an oncologist, so I cannot really listen to this without kicking in. So first of all, if you listen to Dr. Weinberg's argument, he very clearly demonstrated that metastatic disease is not genetic. He showed all of us that there is no gene that is going to be implied and found really in the primary tumor and in metastasis, and he clearly demonstrates that it's an epigenetic phenomenon. So for this part, if you think of cancer also as metastatic disease, then of course your argument is totally correct. That it is not purely the genes, right?
But he didn't start saying that. He was the one who told us.
He did not start saying that, but this year we all heard him that he said it to everybody that this is it.
In a single gene caused cancer. This is 1982. And he, in 2014, told us that he pulled a fast one before Congress to convince them to fund a project that carry billions of dollars of your target, of your taxpayers' money to do something that he knew that was not true, right?
So this year he acknowledged that metastatic disease is not due to genetic mutation. So I think this is an important point. So this is really a foot on which you can stand, because he's mainstream, totally mainstream, right? He's, I think, in the center of the mainstream, and he said it. And then, of course, going from there, you can also discuss other aspects.
I would like to bring up the role of psychological injuries. We've been talking about physical injuries as precipitating cancer. If somebody grows up with 4 psychological injuries in childhood. You know, they're sexually abused, they're emotionally neglected, a parent dies early, and they're bullied at school, they have 2.5 times the rate of developing cancer as somebody who grows up in an emotionally healthy home. And that's not just childhood impacts on cancer, it also occurs in adulthood. Women with strong symptoms of post-traumatic stress disorder have double the risk of developing ovarian cancer compared to people with no symptoms of post-traumatic stress disorder. So I'm a psychologist. I think it's very important to look at the impact of these psychological injuries on the person, and that people with multiple psychological injuries have much higher incidence of cancer than those without.
I totally agree with you, because my colleague Neil Su has been studying epinephrine, right? Those, if you anxiety and the stress, the cancer grew faster. So they clearly there is a system, disease, effect overall grows cancer. But I mean, let me just do, back to Carlos. There is no contradiction, 2 types of genetics. One, McClintock talk about the genome, Mendelian talk about the individual genes. So life is really 2 stages, same as cancer. So those things are not contradiction, or either oncogene or either no gene, because they need to work together side by side. Otherwise, they have no life. That's my comment. Same, otherwise you have no cancer.
If I may address the 2 questions. First of all, I assume that nobody is implying that problems of our minds are mutagenic, right? So
no.
Okay, so that is a point towards the fact that the damage that I forgot, I didn't know who this person was, who said the damage is not mutagenic. The damage, if there is damage, is obviously because of the stress that these women have, and as a result of which some tissues malformation can happen.
Yeah, but those hormones can facilitate the growth of the tumors. So this is a part of the tumor.
Well, but okay. So once again, are you saying that these psychological things cause mutations? Is that what you're saying?
Facilitate growth. Its growth is not everything is mutation. It is a facilitate some growth hormone, not the mutation.
This person raised the point that women who are exposed to stress have more cancer than others. And I said, and I'm asking you, I said that it's unlikely that these problems of the mind are mutagenic. I don't believe they are. I don't know if somebody thinks that they are.
It's not everything happen at the DNA level, okay? Everything, you can have a growth, right? You can have something else. It's not like you have at the DNA and have a mutation levels. So this is why it's so important. It's a 2 stages, okay? First stage is give a birth of a cancer, and then later you need something to make the grow, which is a Mendelian development. So if you look at their life, it's a development. It's an embryogenic process. First 5 days, later you need all of the oncogene activation to become alive, become a human, become a teratoma. So these 2 stages are not mutually exclusive. They need to work together, to form a tumor, form a tissue.
You see, you're always looking for a compromise.
It's not a compromise, because
I believe
it's not a life compromise.
Henry.
It's 2 stages.
Let me say something. So yeah. I don't think every time the subject becomes the same subject of the today's subject is we're talking about the adaptive therapy, because that's the Bob is the expert to offer the information for us, because right now it seems like every time we go back to there. So I'd like to ask Bob's future view. So what is your wish list for the adaptive therapy? So what's you're thinking future? And also, if other people try to follow yours to do this stuff, so what's the most important tips, I guess?
And quickly, before you answer that question about the future of adaptive therapy, Bob, I just want to point out we have about 15 minutes left of this whole thing. I'm going to quickly pop the schedule in the chat. We're sorry about the miscommunication today. Nobody was late, by the way. Just want everyone to know. Everyone was on time. Nobody missed anything. I'm going to pop in the schedule. And our next one is Matthias Mann later today. And take it away, Bob. What's the future of adaptive therapy?
Yeah, I don't really have any grand pronouncements, to be honest. I think that to me, the biggest lesson has been that we need to learn more about the tumor before we start treating it. If we could fill in, key parameters in the equations that govern response, resistance, I think we could develop new approaches, or we could personalize medicine. We could personalize therapy that goes, beyond just getting molecular targets and finding and disrupting them, but also using the evolution dynamics to delay the onset of therapy, or to prevent the onset of therapy, and therefore being I think it's arguable that as the number of treatments become greater, as more and more drugs to treat more and more cancers, and increasingly there's at least one good drug for most cancers, that increasingly, it's clear that what people are going to die because of evolution, because of the ability of the cancer cells to evolve resistance. And so I think increasingly what we are going to be getting into is the fact that we've got drugs, we'll be getting better and better drugs. But now I think is the time to try to use drugs more in a smarter way, and to get away from the sort of traditional, maximum tolerated dose until progression kind of dogma that the oncologists have been using for a number of years, and to really think carefully about these dynamics and how we can intelligently alter the way that we give treatments. And I don't mean just giving one treatment, but giving multiple treatments in different times, and using the evolutionary dynamics of cancer to optimize it. The rule is that an evolving population can only adapt to current conditions, never anticipate the future. Whereas the oncologist can anticipate the future, can control the future, can change the future. And I think that's an incredibly powerful tool that's not been used with the degree of power that it has. So
I have a question for you in terms of the future.
And I hope we can have some impact.
Yeah. I was just thinking of Dr. Hank's question. So where is immunotherapy fitting in this adaptive therapy? Because I'm just that maybe immunotherapy may be the ultimate adaptive treatment, because
absolutely,
at a certain level, the cells.
Absolutely.
Cells.
Sure. Immunotherapy is a predator-like dynamic. It's not precisely like predator, but it has those abilities. And there's evidence that the smaller the cancer population is, the more effective the immunotherapy is. Clearly, you can manipulate the cancer cells to express more antigens, for example, which presumably make them more vulnerable to immunotherapy. We actually just yesterday in a tumor board looked at a patient in whom got immunotherapy early on, which I think is maybe not the best approach, but anyway, and had a hyperproliferative response. So got immunotherapy, the tumor took off. What we then did was take immunotherapy again, but now add a cytotoxic drug, so that it started its hyperproliferative state, and then we targeted that, and so that's some ways that you can spin off of immunotherapy. But I think mostly we view immunotherapy, I'll use a baseball analogy here, as the closer. So for those of you who don't follow baseball, when a team is ahead at the end of the game, you bring in your closer. This is a pitcher that will come in and pitch for an inning or two and win you the game. And we think that immunotherapy should be our closer here. We should batter the tumor. We should get it to we should damage it as much as possible. We should keep it from making an acidic environment and releasing those public domain chemicals that allow it to escape the immune system. We should maximize the amount of antigens that it's expressing, and then bring in the immune system as a closer, as the one that pretty much finishes the game and essentially wipes out the last. So, but that said, I think there's a lot of ways that you can do this. Currently, that's kind of the way that we're looking at it because of this small population.
Following that analogy, the CAR T treatment in tumors, then this is the reason it's not working, right? Because we don't use it as a closure, but we use it as an extinction therapy, and that's maybe why it's not working.
Yes, exactly. In fact, that's precisely one of the discussions that we have had fairly often. That CAR T cells are an excellent example of a potential closer, and really the using it up front. I mean, I guess they have some success in some tumors, but I think that if again, we tend to look at therapies as silos, as single events. Whereas I think that if we could look at them as a continuum and a sequence of events that are put together strategically, I think that the CAR T, at least as it's currently used, would be best at the end as your final blow to the tumor. And I have no wisdom beyond that.
All right. Well, does anyone else have any questions before we close things out? Get your final questions into Bob. This may be your last chance.
Or we could talk about mutations in cancer.
Or we could do that. Go for it. Perry, do you have any final questions for Bob before he talks about his final points?
Well, just I enjoy Bob's your work for this many years, because Bob is truly pioneer so many years to talking about cancer evolution, and at that time he's just a very few people alone in this field, and now this field have grown so much, and we hope with your help to inject some of the evolutionary concept, especially the macroevolution, microevolution, in such a way. Because I remember the years ago, I always ask Bob's advice, and he told me the genetics is too complicated. I only focus on the phenotype, the landscape. So now we still try to get some more information about genome type as well. So thank you, Bob. Yeah.
Okay. Well, thank you, and I enjoyed the session, and a lot of interesting questions and discussions, and thank you for everyone who's contributed.
Well, I'll just chime in and say, Bob, I didn't have the slightest idea who you were a year ago, but then I started hooking up with Henry and hearing about Bob Gatenby. And so it's a real privilege to have you on. And I just want to thank—
You've been talking to my mother.
Well, I just want to thank everybody, and including you, of course, Bob, but for showing up. And there's been such a high level of interest in a level of collegiality, and a level of flexibility of thought that just doesn't seem to be very common. And now everybody's starting to say, well, how do we keep this going? And so, well, we're thinking really hard about how to keep this going. So thank you, Bob, and thank you everybody who's participated on today's call.
Yes, and please join us for Matthias Mann's session today at 2 p.m. Eastern time. We would love to continue this conversation and get Matthias's view on all of this. You will find the entire correct schedule in the first email that you would have gotten from Diane. And from here on out, I am going to be sending reminder emails 1 hour ahead of any of the calls. So you should have already received the invite for Matthias's meeting late today in 30 minutes, just about. So look forward to those emails. Make sure they weren't going to your spam. Let me know if they did. And yeah, we really appreciate you all being here. This has been so fascinating, even for me, a non-scientist.
Thank you. It was nice to see old friends, and it was nice to meet new friends. So take care, everyone. Bye.